Hi, I'm Tate. And I'm Alex. And this is our final circuits design project, the audio preamp. Okay, so we're looking at the volume control here, which is this circuit with R1, R2, and R3, R2 being pot. We can turn it into this circuit with R2 being split between 1 minus alpha and alpha. This circuit makes it fairly clear that you can run R3 and alpha R2 in parallel, measure the voltage across them, and we're running R1, 1 minus alpha R2, and R3 all together in series with these two in parallel. You can get the current running through the whole circuit because it's just Vn, it's voltage drop, and you know all the resistance. And then with that current you can get the voltage drop here, and you can get the voltage drop across the equivalent resistance here, and that's going to be your V out. If we do that, we get a graph that looks like the blue line here, where our theory and our bottom is how far alpha is moved. So it's just a proportion. It could be 100%, it could be 0%. And then our axis here is V out over Vn. And this, since this is our volume gain, you can see it sitting at about 80% for our maximum. There is a similarity in the curve, and they link up at the limiting cases. Okay, we're going to do an intuitive look at the low frequency passing through our circuit. And so the most important thing here is as low frequencies move through a circuit, you can see I have a capacitor here. Its impedance is 1 over j omega c. So lower frequencies mean higher impedance. And that means we're going to get an open circuit for our capacitors. So this is the diagram we're familiar with, and you can see the capacitors become open. And then this really simplifies into a inverting amplifier, because we're going to run negative feedback back through R3 and whatever alpha R2 is set to, R2 being the pot. And that's going to go back through negative feedback, and our initial impedance is just going to be R1, and what I have labeled here is 1 minus alpha R2. And so you can see that here. We have just standard inverting amplifier. V out over Vn is going to be, it's really negative ZF over Zi, but that doesn't matter so much here. And we have R3 plus alpha R2 over R1 plus 1 minus alpha R2. Important thing to note is that if you want alpha to be right in the middle and want no increase in V out over Vn, as in you want this to be 1, for instance, then you actually have to have R3 and R1 be equal in order for the top and bottom to be equal. And if we look at another case where maybe we want 10 volts to be our V out over Vn when alpha itself is 1, then we would have R3 plus R2 over R1. And what that tells us is that if we want this to be 10, then R3 plus R2 has to be about 10 times R1. But we already found out that if we want the middle to be our even spot with no amplification, R1 equals R3. So really what we have is maybe something like R plus R2 is over R is going to be 10 to get our amplification. And so here you can see that if R2 was maybe like 100,000, that we would want our R's to just be something like 10,000. So here we are going to look at the high frequency. We're going to try and get an intuitive idea of how it works passing through the treble part of the circuit. But first, a note about the capacitors. With the high frequency moving through them, the impedance greatly decreases because the frequency is in the denominator. So your capacitors turn into shorts, which means, for instance, in the small picture here of with R2, the pot above and the base control, note that the capacitors here allow a short over that pot when you send high frequency through. So that means that your base pot really won't affect your treble frequencies when you send those high frequencies through this component. They just short over those resistors that are equivalent to the pot. So then if we take a look at the treble component to the circuit, we can see we have V out and Vn. Again, we have this inverting amplifier. And R5 is in both the feedback as well as the initial impedance. And you can work out a simple inverting amp amplifier and find that R5 doesn't affect it. But here what we're going to do is we're going to model this, again, with those capacitors, and we're going to take their impedance into account in our feedback and in our initial impedance. And so what we're going to have is we're going to have R5 plus R4 plus the impedance of the capacitor, so this loop. And we're also going to have then the impedance of the capacitor plus R5. And so that's going to give us our ZF over Zi, which we can set to be V out over V in. Trick here is that you can go into the lab and mess with R5 and R4 because by increasing R5, you can tell the circuit how much current is going to flow through the treble versus the base components of the circuit. And so what we found is that we needed actually a much larger R4 than R2 and set R5 accordingly. And then we could actually find these capacitors. Okay, so here we have the full circuit and all the components. And R1, R2, and R3 at the top, R4, R5, and then R6, and you can see C1, C2, C3, and C4. And then the components are listed here, with R1 and R3 about equal to each other, R2 about 10 times as much, R4 noticeably larger, with R5 being used to balance current traveling through both the base and treble components. Both capacitors, pairs of capacitors being somewhat equal to each other, and specifically C3 and C4 being set so that we have that 10 volt amplification of the high frequencies moving through the treble components. So I'm going to talk a little bit about the transfer functions for this circuit. And so we have the bass control in R1, R2, R3, C1, and C2, and we have the treble control in C3, R4, C4, and R5. We have V in over here, V out, R6, and that is going to be our amplifier. And so simply put, both the treble and bass control are going to be inverted op amps. So they're going to use ZF, or the resistance of the feedback, over ZI, the initial resistance or impedance, in order to calculate V out over V in, which we set to be about 10 at peaks. So if we look at the bass components now, we can look at, for instance, if our pot R2 is set fully on the feedback loop, then we're going to have more feedback than initial resistance, and our transfer function becomes R3 plus the R2 and C2 in parallel, and then all that will be over R1, because R1 is ZI, and this is ZF. And then the way that we handle this in our graphs is we simply made this imaginary, we pulled the imaginary number out, and just said R3 plus 1 over R2 plus omega C2, and put that all over R1. If we want to look at the bass dealing with a mid setting for our R2 pot, we see again we have R3. We can just read this off basically. It's gonna be R3 plus, and then the 1 minus alpha R2 and C2 in parallel. So that's that for ZF, and Z1 is gonna be R1, and then plus the 2 in parallel again. And we see that here. Actually, these J omega C should be in the numerator. And then we're going to put that over, so ZF over ZI. And then if we wanted to set bass to full cut, we have all the R2 and the initial impedance. And so ZF over ZI is going to be R3, because that's ZF. And then we have R1 plus, and then 1 over R2 plus C1, omega J. And then very similar stuff here for the treble cases. We have, the trick here is that R5 shows up in both the feedback and the initial impedance. Here it's going to be C4 and R5 in series, C3, R4, and R5 in series. This is going to be for a treble with full cut, because R4 is on the left side there. If we want full treble, then R4 is going to be, our pod is going to be set entirely into the feedback loop. Then R5 shows up in both. And then if we have R4 split in half, it appears in both. And actually, it's obviously because C3 and C4 were set to 1, it becomes 1 when we're in the middle.
Okay, this is the condition in which we have both tone controls set to flat. As you can see, the theoretical bass component of the circuit is pretty much 0. The theoretical treble component of the circuit wasn't quite balanced well enough, and we have a little bit of boost with slightly lower frequencies. And that reflects in the experimental data as well, where we have a little bit too much boost in lower frequencies, where it wasn't quite balanced as well. We also have a little bit of boost in the higher frequencies with the experimental data as well. Ideally, we could have balanced the circuit better to make the tone control completely flat, but it isn't an audible difference, really, as we heard when we tested the circuit.
So here we're going to detail the optoelectronic communication link, and so what this means is that we're basically going to take in an iPod and send a signal across a LED light to a resistor that will be affected by, its resistance will be affected by the amount of light it receives, and that will affect direct current signal, and we'll be able to read that into our final circuit. And so the idea here is that your iPod will generally output about 1 volt at its peak. And so if we plug the iPod directly into a about 3 volt battery, which we can get from about 2 AAA batteries in series, you'll see that we then funnel that higher frequency, which will peak at about 4 volts, and then the negative 1 volt minimum in that iPod signal will be about 2 volts. And so we picked a blue LED here because the blue LEDs turn on between about 1 and 4 volts. So that means we'll have a very dim signal around 2 volts, but around 4 volts we'll have a very bright signal. So we have that LED. We have a resistor here to protect it, which can be just a small resistor that won't take away too much voltage. And then we ground after the LED. And so this LED will have varying voltage with the iPod's varying AC current. The battery there is applying that voltage up to what it needs to be to turn the blue LED on. And then our light affected resistor here will be hooked into a battery, and that's going to be about 1 volt because it just needs to be 1 volt in the peak in order to have our circuit catch it with a V in, and then it can go to our volume control and then our tone control.
Hi, I'm going to demonstrate our preamp circuit in operation right here. As you can hear, there's a song playing. This potentiometer right here controls the volume. And as you can see, as I turn it up, we get a boosted volume. You can turn it all the way down to get the song cut out. We also have separate bass and treble controls. This is the bass control. Go ahead and crank it up. You can see the bass frequencies, the longer waves are jumped up now, and as I decrease, the blue is the output. The blue wave is going to be decreased for the longer frequencies, or longer wavelengths. Sorry, lower frequencies. Also, for the treble control, we have boost and cut. There's treble boost. You can see the shorter frequencies are now getting boosted on the blue line, and that's full treble cut.
Here we know there's our it's slowing out for us in it. Yes, now.